Okay, welcome back. This one's arc length and then surfaces of revolution. Um, right, so 7.4 arc length and surfaces revolution. So basically trying to find the length of a curve. And then the second part is finding the surface area of these regions that are being generated by rotating other regions about axes. Okay, first, more importantly, in my opinion, is arc length. Okay. So for arc length, for this formula to pan out for us, we're going to need two things. So some required intel. Firstly, the mean value theorem, which was theorem 4.4, mean value theorem, which you probably remember it in its graphical type version. There's obviously requirements for this to pan out. You need F continuous on a closed interval, and then differentiable on the open interval. And if you have all that panning out, then there will exist this number. So graphically, what are we saying? If you have this function on this interval from A to B, and I don't know what it's doing, maybe it's going like this, there will exist some C value in between A and B such that the slope of the tangent line at this point C is equal to the slope of the secant line through A and B. Okay? In math symbols, there will exist a C in this open interval from A to B such that the slope of the tangent line at C, in other words, if you take the derivative of f at C, it'll equal the slope of the secant line through A and B. Oops, it should be f of B minus f of A all over B minus A. Okay. So that's one thing we need. The second thing, of course, we need is this distance formula. And then maybe make a note about the distance formula. So you remember what the distance formula was. Distance for 2 points in a plane, so x2 minus x1 squared plus y2 minus y1 squared. And then kind of note that there's this weird relationship between this and the slope formula. If you were to factor out an x2 minus x1 squared from this thing, it would look like this. Okay, so then it would be 1 plus y2 minus y1 all over x2 minus x1 squared times 1, no, just x2 minus x1. Okay, if you factored x2 minus x1 squared out of the root, you get this. And then this thing right here, look at that. This is a weirdness, a weird peculiarity, right? That thing right there is a slope formula, right? Slope. So there must be some weird connection between slope and distance. Anyways, there's that. So taking all this information together, we can finagle a formula for the length of a curve, the arc length of a curve. So let's go ahead and attack that problem. So part B here is kind of our derivation. Let's see what we're working with. So I have some sort of curve in the plane. I'm worried about figuring out the length of this curve from A to B. And one observation is that you could cut it up into a bunch of little lengths and then maybe apply a ruler to it and figure out the lengths of all these little lengths. Okay. and then add up those little lengths, and that would tell you a good approximation of the curve, right? So what am I doing here? I'm taking the sum of all these little lengths, and to figure out the lengths of those guys, you're just going to do distance formula. Okay, so maybe in particular we had these 2 points here. Let's call them this first guy x sub I minus 1 comma y sub I minus 1 is this guy, and then this guy will be x sub I comma y sub I. Okay. And then dump them into this formula with the distance formula. So we got x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 in our room squared. And then we're going from I equals 1 to n. Okay. And that'll give us an approximation for the arc length. They always use the letter S for arc length. Okay. Okay. So this thing then we can kind of turn into a Riemann sum. The Riemann sum always has this change in x thing over here. And change in x is really just a difference between x sub I and x sub I minus 1. So if I pull this trick here, I can kind of get a change in x out here. And on top of that, I'll have this kind of slopiness formula. And on top of that, this little formula could then be replaced by a derivative. Okay, this f prime of c, given all of those little conditions that we hope apply, right? So, anyways, let's do that. So I have a sum from I equals 1 to n, and I'm factoring out x sub I minus x sub I minus 1 squared. I'll be left with this critter. Okay, so it'd be y or 1 plus y sub I minus y sub I minus 1, which you could also think of as f of x sub I minus f of x sub I minus 1 all over x sub I minus x sub I minus 1, all of this squared, and then times x sub I minus x sub I minus 1 on the outside. And then this thing is a change in x element, and we'll have a Riemann scenario going on here. Right, so this thing will become the sum of I equals 1 to n of the square root of 1 plus, and we could replace this business via the mean value theorem with the derivative of the function at some c sub I in the interval between x sub I minus 1 comma y sub I minus 1 and x sub I comma y sub I. And then times this other thing, which we could just call change in x. Okay. Alrighty then. Once you get there, you're ready to take the limit and then get our final formula. So taking limits under suitable conditions, s then will equal the integral of the square root of 1 plus f prime of x dx from a to b. Okay. So hopefully you can remember this formula. It's just a matter of, if you're dealing with arc length, you're dealing with distance, so you must be dealing with square roots. And then there's this connection between the distance formula and the slope formula right here, where derivatives you can always kind of think of as a turbo version of slope. Right? So anyways, there's our formula for this section. I think we just want to look at a couple maybe problems associated with it, and then we'll look at surface area, which uses arc length in it. So number 9, we have y equals x to the 5th over 10 plus 1 over 6x cubed, and then we're on the interval from 2 to the 5. Okay, so I need some information. I need f prime. Whoops, and this should be squared. I totally apologize. That was a major mess up on my part. Yeah, so sorry about that. Should be squared. All right, so anyways, I need the derivative of this, and I need to square it. So the derivative, y prime, power rules bring down the 5, so it'd be 5x to the 4th over 10 In other words, x to the fourth over 2, and then plus, what is this thing? And its other forms, it's 1/6 x to the negative 3, right? So bring down the negative 3, you get negative 3/6, which is the same as negative 1/2, and then x to the negative 4. So it ended up being negative 1 all over 2x to the fourth, which I could rewrite by factoring out a 1/2, I guess. I don't know if that's going to help life any, but let's factor out a 1/2. And then we get x to the fourth minus x to the negative fourths. Right? We need to square this thing when we plop it into our fancy arc length formula. So this thing squared is equal to this thing squared. So it'd be 1/2 squared is 1/4, and then this thing squared, we have x to the fourth times x to the fourth is x to the eighth. Those are the first, the outers, minus 2x to the 0, x to the fourth plus x to the negative fourth is x to the 0, x to the 0 is 1, so minus 2, and then plus x to the negative eighths, right, when I FOIL. Let's plop all that into now our fancy dancy arc length formula. So I'm going from 2 to the 5 square root of 1, and then plus this business plus 1/4 times x to the eighth minus 2 plus x to the negative eighths dx. Okay. We could factor out a 1/4 from all of that character. So we end up with the square root of 1/4 times 4 plus x to the eighth minus 2 plus x to the negative eighths dx. The square root of a product is the product of the square roots, so we end up with a 1/2 constant. I can remove that from the integral, times the square root of 4 minus 2 is 2, and then x to the eighth plus x to the eighth. But that's a lot like this thing right here. Right? And as a matter of fact, it's just this squared, but with a plus in between. So we'll end up with x to the fourth plus x to the negative fourth squared, which is very, very convenient because now I can take the square root of this thing and then integrate via the power rule. So I'll have this equaling 1/2 integral of x to the fourth plus x to the negative fourth dx, and I'm ready to rock and roll. Okay, so this will be 1/2 x to the fifth over 5 minus x to the negative 3 all over negative 3. I need to evaluate that eventually. This will then be 1/2 times x to the fifth over 5 plus 1 all over 3x to the third. And I'm going from, what did I say, 2 to the 5. Okay. Plug that in. It's not going to be pretty. So 1/2 times, this will end up being 625 minus 1 over 375 minus 32/5 minus 1 over 24. And I just put that into my calculator. I got 309.3195. Okay. So where might you see this in the real world? I was asking around. I said maybe when you're figuring out the length of cables, and on top of that we have some hyperbolics floating about in those kind of scenarios. So here we have some telephone poles. We'll put those about the x-axis, or located about the y-axis. So 2 telephone poles. Here's my y-axis. So I should draw it like that. Something. The cable between them is drooping down like this, but it's symmetric on both sides. We can model this cable using the formula y equals 20 cosh of x over 20 Okay, so this point right here will be 0, 20. The location of the poles is at -20 and then +20. What else? I guess that's about all we want. We want to know the length of this cable. Okay, so to use our arc length formula, I need the derivative of this thing. So y prime is going to be 20 sinh of x over 20 times the derivative of the guts. So times 1 over 20. 1 over 20 times 20 is just 1. So I got sinh of x over 20. Okay. One other thing we need is an identity. And so just note our sort of Pythagorean counterpart for hyperbolics would be cosh x minus sinh x equals 1. So we'll probably need that eventually. Okay, fine. So my arc length is going to be the integral. And because it's symmetric, I'm going to chop it in half. I'll just go from 0 to 20 and then multiply the outside by 2. Okay. And then I had the square root of 1 plus the square of the derivative. Right? So sinh of x over 20 squared dx. Okay, so this thing I can simplify using this expression. If I just add sinh over, this thing equals cosh squared. Right? So this will be 2 integral square root of cosh of x over 20 squared, and then I can get rid of the square root. So that square root is always a troublemaker in integrals, and we'll go about looking for ways of getting rid of the square root. Anyways, we have 2 times the integral now of just plain old cosh of x over 20 dx. Cosh. You do a u sub, but the constant that'll end up floating around will be a 20. So you'll end up with 40 times the integral of cosh of u du. And then the integral of cosh is just sinh. So we get 40 sinh of u. And let's back substitute. So we get x over 20. And then we're evaluating from 0 to 20. Right? So if I plug in 20, I'll get sinh of 1. So I got 40 times sinh of 1 minus sinh of 0. And then remember what sinh is. It's just e to the x minus e to the negative x over 2. So this would be 40 times e to the 1 minus e to the negative 1 all over 2. And then minus e to the 0 minus e to the negative 0, which is just e to the 0 minus e to the 0 all over 2. This will be 0, so it's equal to 20 times e minus 1 over e when all is said and done. That's approximately 47, and we're dealing with meters in this problem, so it would be 47 meters. Okay, great. We are worried about areas, surface area now in this section, and we can use this arc length formula in order to produce the formula for surface area. So let's take a look at that real quick. Area of the surface of revolution. Okay. So let's get back to our Riemann sum and kind of look at what our running man is accumulating this time. Let's take this thing, and again, we're rotating it about the x-axis, and we're going to get kind of a base object, but now we want the surface area of that base. Okay. So this time we're using like what will essentially be little strips of paper, kind of. Okay, so we're taking this region here and then looking at the surface area of that region, and we have a formula for that. It's like a piece of a cone, basically. So let's take a look at what it looks like. Look like this. Okay, we need a formula for that object for our running man to accumulate. So our little criminal is accumulating the surface area of all these objects in this direction. So it's the sum of s sub i's this time. Right. We just need a formula for this s sub I thing. So to get this formula, what we need is basically this, the length of the curve here, which we can get from the arc length formula. And then we need basically the radius of this object, quote unquote radius. Okay, okay, so you know, it's going to be 2 pi. The formula for the surface area of this thing is probably not as well known as maybe like the volume of a cylinder or something like that. But there it is. It's 2 pi RL, and then the R is just going to be sort of the F of x sub I, or whatever particular location we are at. So 2 pi f of x sub I, and then the L formula would be the square root of 1 plus f prime of c sub I squared, where c sub I is some value in between x sub I minus 1 and x sub I, or something like that. Okay, but it's basically the formula from the last section we were looking at. That will give you this part of the surface area formula. So if the running man is zipping across and stealing up all of these guys, what we end up with is you know, the sum of these s sub i's, and then we want to take the limit as the number of these things goes to infinity, or this dimension goes to 0, and of course that will give us our integral. It'll be 2 pi f of x times the square root of 1 plus f prime of x all squared dx, and it's going from whatever to whatever, a to b in this case, right? Okay, so this thing then is our formula, and of course we'll worry about other orientations in the homework. I'm not going to go through any of those. Let's just look at one of the problems, and hope that'll be good enough. I won't be putting surface area on the test. Okay, so anyways, y is the cube root of x plus 2. And let's see the region. The book is telling us the region, I think, this time. So where is it? Trying to find the region. I'm going to have to look it up because my notes are so bad. Let's see what section we're on. Must be section 7. And, yeah. Today is 43. Rotating about the y-axis, at least. And I think we're going from 3 to whatever the heck it's at, 4. So 1, 2, 3, and then 4. So when and I'm going to need the other, I think, formula, but one thing at a time, I guess. Looks like they want x is 8. Yeah. So 1. At 1, this thing will be, cube root of 1 is 1, plus 2 is 3. So it'll be right here. 2, 3, 4, 5, 6, 7, 8. And then at 8, the cube root of 8 is 3 plus, 2, and then plus 2 is 4. So it's this region they're worried about right here, this little sliver region. And they're rotating it about the y-axis, okay? And they want the surface area of that thing. Okay. Alrighty then. So I needed it's a weird orientation. It's not this x-axis orientation, so that's kind of troubling. I needed to kind of back engineer it all right. So in particular, my running man now is stealing his volumes in this direction. So let's see if I can draw a little rectangle in there for what I'm after. So here's one of my little sort of rectangle-ish thingamajigs. I need a radius function, which will be just this distance from here to here. And then I also need an arc length function, which is kind of this distance from here to here. So it's in terms of y. So I'll have some L, I guess we'd call it L of y function. In this case, I'm going to need to rewrite this in terms of x, or sorry, in terms of y. So if I solve for y, I'll have cube root of x equals y minus 2 cubed both sides, so x equals y minus 2 cubed. Okay, so my L of y formula will be the integral of 1 plus the derivative of this with respect to y. So that would be, let's see, x prime is 3 times y minus 2 squared. Okay, so I'm plopping that into here. So what do we get? 3 times y minus 2 squared squared. And then I also need a radius function from here to here. It's this distance. Do I really need that? I mean, I think I could just use the distance from here to here. I don't need to necessarily worry about anything kind of in between business here. So I think I could just worry about this distance. Okay, I don't need to, because this region, when I do rotate it, it's going to kind of look like this object where the y-axis is sitting right here. Okay, if you want to put some dimension in there, it'll look like this. Okay, and it's not, you know, it's not this dimension I'm after for the radius. It's this dimension from here to here that I'm after. So yeah, I'm not going to be considering this little hole part. I just go from here to here, and that formula then is not so bad. So let's call that, I don't know, a radius function, r of y, and that'll just be given by this guy, whoops, this guy here. So that would just be the y minus 2 cubed. Okay, so at the end of the day, it looks like what we're getting is 2 pi times the integral from 3 to 4 of y minus 2 cubed times the square root of 1 plus 9 times y minus 2 to the 4th dy. But like I said on the test, I'm not going to worry about the surface area ones. You'll want to go through them in the homework, get practice doing integrals like these, obviously. But okay, that's enough of that. Okay, so we'll see you next time.